Hello, this is Dimitri Bertsekas. Let me welcome you to the second of 5 lectures on semi-contractive dynamic programming. This subject relates to a type of dynamic programming model that has many applications and where some policies are well behaved in the sense that their dynamic programming mapping has a contractive-like character, while other policies are not. Okay, so let us now briefly review the contents of the lecture series. In the first lecture, we discussed various examples where the semi-contractive behavior manifests itself. The examples were from broadly applicable types of problems, such as shortest path problems and linear quadratic optimal control. In this lecture, we're going to provide a mathematical framework that explains the semi-contractive behavior, and we are going to restrict ourselves to stochastic optimal control problems. In the next lecture, we're going to generalize the results of the second lecture to more general abstract dynamic programming models. Then we're going to discuss applications of the theory to various types of models such as stochastic shortest path and other types of problems. Then we are going to talk about algorithms such as value iteration and policy iteration. In this lecture, we're going to deal exclusively with the stochastic optimal control problem that we have also discussed in the previous lecture. It involves a discrete time dynamic system where xk denotes the state at time k, uk the control at time k, and wk is a random disturbance with given probability distribution. The next state, xk plus 1, is determined from the current state, the current control, and the current disturbance according to this equation. The random disturbance has probability distribution that depends on xk and uk exclusively, and we make no assumptions on the spaces x, u, and w, other than the fact that w, for mathematical reasons, we assume it to be a countable set. We consider policies, which are sequences of functions of state to control that satisfy certain constraint that depends on the current state. And given a policy, if we consider the cost function over an infinite horizon as measured by a cost per stage function g, the cost is discounted by a discount factor alpha, which is between 0 and 1, or could be equal to 1 in the undiscounted case. Now, the k-stage cost is given by this expression, but it's a random variable, so we take its expected value, and then the limit as k goes to infinity gives us the cost of policy pi starting at initial state x0. So, this is a function that depends on policy and state. If we optimize over policies, then we obtain the optimal cost starting at state x0. An optimal policy is one that attains the infimum in this equation for all x simultaneously, and a lot of our analysis deals with stationary policies, which are of the form where the control function does not change over time. We will now review some basic concepts. The cost of a stationary policy is mu starting from state x, which we denote by j mu's of x, and the optimal cost starting from state x, denoted j stars of x, typically satisfy Bellman's equations. These are fundamental equations. This equation corresponds to mu, this equation corresponds to the optimal, and there's one equation for every x. They can be viewed as functional equations for the functions j mu and j star, and they are quite long and complicated equations, so it's very helpful to use some shorthand notation. And the notation we are going to use is to take this expression here and write it as h of x, u, and j as a function x that depends on x, u, and the function j. And then we introduce the mapping is t mu's of j by this equation, and tj using this equation. J is a function. T mu's of j is also a function whose value at state x is given by this expression. And we can look at Bellman's equation and see that they can be written abstractly as fixed point equations. J mu is a fixed point of this mapping T mu, and J star is a fixed point of this mapping T. Semicontractive problems are those for which some T mu are well behaved, have a contraction-like structure, and others are not. Let us also review the kind of results that we aim for in total cost stochastic optimal control. The first question is the characterization of the solution set of Bellman's equation. We want to know if J mu and J star are solutions of this equation, and also whether there are some other solutions, or whether J mu and J star are unique solutions. There is a necessary and often sufficient condition for optimality, whereby we want to show that if mu stars of x attains the minimum in this expression for all x, then the policy mu star so constructed is optimal. There is a shorthand way to express this. If this equation holds, then mu star is optimal. We have the value iteration method that starts from some initial function j and then generates t sub j, t squares of j, and so on. In other words, applies the dynamic programming algorithm many times. And we want to know that as number of times goes to infinity, whether this algorithm gives you in the limit j star. The policy iteration algorithm operates on policies rather than functions and generates a sequence of policy mu k. And what we aim to show is that the sequence of policy cost functions converges to j star, is asymptotically optimal. And the method operates in two stages per iteration. In the first stage, given the current mu k, we evaluate by solving the corresponding Bellman equation to find j mu k, and then we stick j mu k into the minimization in Bellman's equation and obtain a new policy j mu k plus 1, and we continue this way. In the first lecture, we gave 4 pathological examples where strange things were happening, such as j star not being a solution of Bellman's equation, or value and policy iteration behaving in a strange way. We want to ask the question, what's the root of all anomalies? And an answer to this is that there are some policies that are not well behaved in terms of value iteration. In other words, value iteration using the Bellman equation for those policies does not converge to j mu, the cost function of the policy mu. In more concrete terms, we saw that such not well behaved policies arise in shortest path problems, as policies that involve zero-length cycles, or policies that are unstable in linear quadratic problems. Now, we want to investigate mathematically how these policies cause difficulties, and we will call these policies irregular in a well-defined mathematical way, and we are going to introduce assumptions and analysis under which we can assert that these policies are harmless. Our general approach is going to be as follows. We're going to select a class of well-behaved or regular policies, then consider a restricted optimization problem where we optimize over the regular policies only. We show that this restricted problem has nice theoretical and algorithmic properties, and then relate the optimal policies of the restricted problem to the original problem, and under reasonable conditions, we're going to obtain strong theoretical and algorithmic results. The mathematical analysis for all this, in much greater detail that we're going to discuss here, is contained in this research monograph. Chapter 3 and to some extent Chapter 4 of this monograph have been updated, and they can be found online at my web page, and I strongly urge you to look at these chapters as an aid for understanding what follows in these lectures.
Let me give an outline of this lecture. We're going to first define mathematically
regular policies. And the definition is going to be relative to a set S of functions J, and we'll explain this a little later. Then we're going to consider a restricted optimization problem where the optimization is done over the S regular policies only. We're going to analyze this problem by using policy iteration ideas, and to this end we're going to introduce weak and strong policy iteration properties of the set S, and we're going to obtain corresponding results that are weaker or stronger. These results relate to the solutions of Bellman's equation, the convergence of value and policy iteration, and the optimality conditions. We are going to demonstrate these results with two examples. One is a stochastic shortest path example with a finite number of states, and the other is a deterministic optimal control problem with an infinite number of states. We will now give a mathematical analysis, and to this end we introduce some notation for cost functions. We denote by R the set of real numbers, and by R sub x the set of real valued functions over the state space x, and by E sub x the set of extended real valued functions over x. So J sub x here can take not only real values but the value plus infinity and minus infinity, and this is necessary because in various theoretical contexts this can happen, although in practice it may not quite happen. In theory and analysis it can happen, and we need to introduce this notation. Let us call J bar the function that's identically 0, and let us give a mathematical expression for the end stage cost of a policy starting from x, and upon the last nth stage we have a terminal cost function which contributes to the cost, this terminal expression that depends on the terminal state, and is also discounted by alpha to the n. Now if you look at this expression, T sub j is just one cost per stage plus the terminal cost. T square sub j is what I'm going for two stages and then taking the terminal cost, and T mu n sub j starting at state x is the result of starting at x and going for n stages and then incurring this terminal cost. So we have this shorthand expression for finite horizon costs. Now if in place of j you use j bar, the 0 function, then this expression becomes what you see here, and this is the k-stage cost of policy mu starting from x with 0 terminal cost, and we can write the infinite horizon cost of policy mu starting from x by taking the limit of this k-stage costs, and this is what we have called j mu sub x. Now let us introduce a very basic definition for our purposes, the notion of an S regular policy mu. The definition is as follows. Given a set of functions S, extended real valued functions over the state space, we say that mu is S regular if it satisfies two properties. The first is that J mu is a fixed point of T mu within S. It satisfies this equation, and J mu belongs to S. The second is that if we iterate with T mu on any function J in S, and in the limit we are going to obtain J mu. In other words, no matter where we start within S, value iteration using this T mu mapping gives us the same result, J mu. Now we say that a policy that is not S regular is S irregular. So a policy can be either S regular or S irregular, and here are two examples. This policy here is S regular. This is the set S, and it satisfies the defining properties. J mu belongs to S. It is an equilibrium point of T mu, a fixed point of T mu, and starting at any point J within S, we converge to this unique equilibrium point. So that's the regularity property, being a stable equilibrium of T mu within at least the set S. Mu bar is not a regular policy, and this can happen in a number of ways. J mu bar, for example, may be outside of S, or it may be inside of S, but starting from some J inside of S, we go outside of S, and we don't have convergence. So the S regular mu are the ones for which J mu is a unique and stable equilibrium within S, and also are well behaved with respect to value iteration, at least for starting points within S. Let us give a graphical illustration of S regular and S irregular policies. And we're going to do this for the case where S is just the real line. So here we have just one state. X consists of just one state. And we're going to use figures like that because they're convenient and also are intuitive. In this figure, we use J is on the horizontal axis, and T mu J provides the graph of T mu. It's a function of J, the scalar J. And when considering fixed points of mappings like T mu or T, it is useful to consider the 45-degree line here. Every point where the graph crosses the 45-degree line is a fixed point of T. So if you look at this blue mapping T mu, this is R regular because within this set S, J mu is the unique fixed point, and also starting from any point within S, like for example this point here, how will value iteration work? Well, from this point, this starting value is going to pick up T mu's of J, and then it's going to go over here to the 45-degree line and go down, and that would be, if this is J0, this is going to be J1, then J2, J3, and so on. The way the slope of this blue function is, you're going to have convergence to J mu from any starting function, either from above or from below. It's going to value iteration is going to converge like so. And this can be traced to the fact that the slope of this function is less than 1 uniformly, so it's a contraction mapping. The red functions correspond to mappings T mu that are not regular. For example, this one here is not regular because it doesn't have any equilibrium point, any fixed point within the set S. This function here is does not correspond to an S regular policy because it has two fixed points. This mapping T mu is also not S regular for the following reason. Even though it has a unique fixed point, you can check that because the slope of this graph is greater than 1, this mapping is not a contraction mapping, and if you consider value iteration starting from any point within S, then it's going to diverge either from the right or from the left of the fixed point. So the blue function satisfies all the conditions of the definition of S regularity. The red functions are not. Now let us consider some examples of S regular policies in the context of stochastic optimal control involving a discrete time equation and a cost per stage over an infinite horizon. Recall the definition of S regularity, and one can prove that if the mapping T mu for a given policy mu is a contraction mapping over the set S, then mu is S regular. This applies to the case where S is a subset of real valued functions and T mu maps S into S. In other words, if J belongs to S, T mu of J also belongs to S. And T mu also has the property of shrinking the distances between any two functions in S. Given any two functions J and J prime, the distance between T mu of J and T mu of J prime is smaller than the distance between J and J prime. Here beta is a scalar between 0 and 1, and this is a norm. Any norm would qualify, any norm over the set of real valued functions over X would qualify to make this a contraction mapping. However, in dynamic programming, typically the norm used is a sup norm or some kind of a weighted sup norm. Now, if you consider shortest path problems that have n states, either deterministic or stochastic, and if you take S to be equal to Rn, the set of functions over the n-state state space, the S regular policies are precisely the policies that terminate, reach the destination in finite time for deterministic problems for any initial condition, or reach the destination in expected finite time for the case of stochastic shortest path problems. So termination and contraction and regularity are very closely tied together in stochastic shortest path problems. In particular for deterministic problems that involve cycles and where a policy does not terminate, then that policy would be SV regular, and we're going to see that it causes problems in the analysis. In linear quadratic problems, we don't use a contraction type of property for policies to view them as regular. Instead, we will view as regular policies the ones that have a stabilizing property, that the linear policies that stabilize the closed loop system. Such policies turn out to be S regular, where S is the set of positive semi-definite quadratic functions. This is a particularly favorable set for the linear quadratic problems because it contains the optimal policies as well as the cost functions of any policy, any stationary policy, which is linear. Let us also illustrate some of the fine points of the definition of S regularity. Whether a policy mu is S regular or not depends on the choice of S. In other words, mu may be S regular for some choices of S, but not for others. S is not part of the definition of the problem. You have to choose it properly so that good results can be obtained. As an example, let us consider a policy mu whose mapping is T mu, and we take here S to be just the real line, or rather a subset of the real line. Suppose that T mu has graphed this blue curve here. So it has two fixed points. One is this one, and the other one is this one here. Suppose that we choose S to start to the right of this second fixed point. So this is S. Then J mu is J mu is obtained from J bar, and it's obtained as the limit of T mu of K J bar, and it's this one. And J mu is such that S regularity is satisfied from it is the unique fixed point of T mu within this set S, and also it's well behaved with respect to value iteration in the sense that starting at any point within this set we converge to J mu, not just from J bar, but from any point. And the same thing starting from a point to the right of J mu. Value iteration operates like so and converges to J mu. However, suppose we change S and we extend it to the left so that it includes J tilde. Then mu is not going to be S regular, because T mu is going to have two fixed points within S, and the definition is violated. Okay, now let us consider restricted optimization over the set of S regular policies. Given a set S, let us denote by M sub S the set of all S regular policies, and let us minimize the cost function over this set. This is what we refer to as the restricted optimization problem. Let J star S be the optimal cost function over the S regular policies only. In other words, Js star is given by this expression for every x. And graphically, representing J on this line here, and let S be this set of functions. Now, the regular policies have cost functions that are within this set by the definition of regularity. So all of their cost functions lie within this set, and the value that is all the way to the left is J star sub S. It is the infimum over all these J mu functions. It can be approached arbitrarily close by some S regular mu. Now J star is the infimum over all policies, so it's the infimum over a larger set, therefore it is smaller than J star sub S. So J star lies to the left of J sub S. They could be equal, or there could be strict inequality between them. We have this relation. Now let us look at an important result around S regularity. Suppose we have a set S, and let us consider the restricted optimization problem and its optimal cost function. And let us look at this figure. J lies on the horizontal axis, and we have this region here that on the right is demarcated by the largest function in S, and on the left it's demarcated by Js star. What the theorem says is that if Js star happens to be a fixed point of T, then this region has nice properties. In particular, here is the proposition: assume that Js star is a fixed point of T. Then Js star is the only fixed point of T within this set, which we call the well-behaved region Ws. Look at the definition. It is the set of all J that's demarcated on the right by the largest value in S, the largest function in S, and on the left by Js star. The second result is that value iteration works well within this well-behaved region. In other words, if you start value iteration within W sub S, then you get convergence to Js star. Not to J star necessarily, but to Js star. Third, there is the standard optimality condition for the restricted problem. It says that if mu star is S regular and Js star also belongs to S, and mu star attains the minimum in Bellman's equation when Js star is used in place of J star, then mu star is optimal for the restricted problem. Conversely, if mu star is optimal for the restricted problem, then mu star attains the minimum in Bellman's equation. Okay, let us prove this result about the well-behaved region. The well-behaved region is Ws, which is shown here. It's demarcated on the right by the largest J in S, and on the left by the optimal value of the restricted problem, which we assume that's a fixed point of T. And the first thing we want to show is that if we start value iteration from anywhere in this well-behaved region, we are going to converge to JS star. So here's the argument. Let's take any starting function j within the region WS, so that this j is bounded on the left by JS star and on the right by some j tilde in S. Now let's take any S regular mu and write the following inequality relating to value iteration. Value iteration applied on JS keeps us at JS star because JS star is a fixed point of t. Now j is larger than JS star, so by monotonicity of t to the k, I have this inequality, and j tilde is larger than j, so I have this inequality as well. And I also have that this is less than t mu to the k j tilde, because t is the infimum over all mu of t mu, so this inequality clearly holds. Now, because mu is S regular and j tilde belongs to S, if I take the limit here as k goes to infinity, what I will get is j mu. And if I take the infimum over all mu that are S regular, I'm going to obtain j star. So in this inequality, taking limit as k goes to infinity and then minimum over mu, the right-hand side collapses to the left-hand side, and in the middle we have that the value iterates converge to JS star. Okay, so the next result is to show that JS star is the unique fixed point within this well-behaved region. If you had a J prime, another fixed point of t that belongs to WS, then we can just start value iteration at J prime, and that will not move J prime because it's a fixed point of t. So we get J prime is the limit of t to the k J prime, which is equal to JS star by the convergence of value iteration result that we have shown in earlier here. So JS star is the unique fixed point within this well-behaved region. Okay, now let's prove also the optimality condition. Suppose that mu star satisfies this condition, attains the minimum Bellman's equation when JS star is in place of J star. Then we have that this relation, because J star is by assumption a fixed point of t, so this is equal to J star, so I have this. And now I have this relationship here with JS star being an element of S and mu star being S regular. This implies that JS star is equal to J mu star, because T mu star has only one fixed point within S, and that is J mu star. Thus, J mu star attains the optimal value of the restricted problem, and therefore it is restricted problem optimal. Conversely, suppose that mu star is restricted problem optimal, then we have, of course, that J mu star attains the optimal value. So this equality holds by the fixed point property of JS star, which is equal to J mu star, which is equal to T mu star J mu star, because mu star is S regular, which is equal to T mu star JS star, because this equality holds. So for a restricted problem optimal mu star, I have that this is equal to this, which is what I wanted to prove. Let us consider now the deterministic shortest path example of the previous lecture. Here we have a very simple graph. There is only one node other than the destination. So the set of states x is just one, just a single state. The destination is cost-free and absorbing, so all the cost functions have zero value at the destination. So we discard that. Here at the state 1, there's a choice between two controls. One is the control U that takes us straight to the destination and costs B, and the other is the control U prime, which keeps us at 1 and costs 0. So there's a zero length cycle here, which is causing all the problems. There are two corresponding policies. The policy that applies U is denoted by mu, has cost equal to B, and it is regular, S regular. You can easily verify that because the terminal cost function doesn't matter since after one step we're going to be at the termination state. The policy mu prime has cost 0, and it is S irregular. The optimal cost, of course, is the minimum between the two. It's given by this expression. Bellman's equation has this form. It's the minimum of between the two controls, B and 0 plus J sub 1. So you can see now that the optimal cost is a fixed point of t, and the set of all fixed points is the set of all scalars that are less or equal to b. And there are two cases to consider here. In the first case, b is negative. In this case, the regular policy is optimal, and we have j star equal to j, s star equals to b, and the cost of the irregular policy is 0. The well-behaved region is this red region to the right. The set of fixed points is the black region to the left. And we can see that the theorem applies. Js star is the unique fixed point within the well-behaved region. In this case, it happens also to be equal to j star. So j star is the unique fixed point within the well-behaved region, but of course there are other fixed points outside the well-behaved region. Value iteration also works from anywhere within the well-behaved region. It converges, in fact, it converges in just one step, you can see. Let's consider the other case now, where B is positive, and it is the irregular policy that is optimal. So J star is strictly less than JS star, and the well-behaved region is smaller, and the set of fixed point contains J star in its interior. As a result, value iteration cannot converge to J star unless you start at J star. On the other hand, value iteration will converge from the well-behaved region. In one step, in fact, it will find JS star. So that's illustrates the theorem in how anomalies, even though anomalies can occur here, with J star not being the unique fixed point and also not being found by value iteration, there is still a theorem that says that you get convergence of value iteration at least for J within the well-behaved region. We have shown that if Js star sub s is a fixed point of t, then nice things happen with respect to Bellman's equation and the convergence of value iteration. But now the question is, how do we choose S so that Js star is a fixed point of t? And there are several approaches for that. One approach is to choose S so that Js star, the restricted optimal value, is equal to J star, the optimal value, and prove that J star is a fixed point of t. Now, how do you prove that? Well, it turns out that J star is a fixed point of t for several broad class of problems generically. For example, in all deterministic optimal control problems, it is generically true that J star is a fixed point of t. There are also stochastic optimal control problems where this is so. For example, cases where the cost per stage G is uniformly non-negative or uniformly non-positive. J star is also a fixed point of t generically for some other types of dynamic programming problems, such as minimax control problems and other problems. But we are not going to look into this issue because this takes us in a different direction than where we want to go. If you look at the revised chapter 3 of the Abstract Dynamic Programming book, you'll see several results of this type. We are going to follow here a different approach that's based on policy iteration arguments. Now, this approach applies when S is well behaved with respect to policy iteration. Roughly speaking, what we mean here is that starting from an S regular policy mu0, policy iteration can generate S regular policies exclusively. Now, the significance of this policy being S regular is that if you have a policy iteration generated sequence of S regular policies, then the sequence of cost functions is monotonically non-increasing. In other words, under S regularity, we have a cost improvement property. So these costs of the generated policies are improving and they are moving towards JS star. They have a limit, and it turns out easily that this limit is a fixed point of t, and also it is equal to JS star. So policy iteration provides a good starting point if we can choose S so that I have good properties with respect to policy iteration. That gives me some results. So let us flesh out now the approach of proving that JS star is a fixed point of t based on policy iteration arguments. If a policy sequence is generated by policy iteration and consists of S regular policy, then it has a cost improvement property. In other words, the new policy is better than the preceding policy, and all of them, of course, lie to the right of JS star, which is the optimal value of a restricted value over the S regular policies. So let's prove this policy improvement property. For mu k, I have that J mu k is a fixed point of T mu k, so this is true. And T is the infimum over all mu of T mu k, so this inequality holds. And by the way mu k plus 1, the improved policy, is generated, I have this equality. T mu k plus 1, J mu k is equal to Tj mu k. In other words, mu k plus 1 attains the minimum in Bellman's equation when J mu k is used. So I have this relationship by definition of mu k plus 1. And now what's happening is that J mu k is greater than T mu k plus 1 J mu k. In other words, T mu k plus 1 applied to J mu k takes it down, takes it to a lower value. By monotonicity of T mu k plus 1, it follows that every time that I apply it to J mu k, I get even lower value. So the limit as so the sequence of t to the mu power of mu k plus 1 J mu k is monotonically non-increasing, so it converges to a limit, and that limit is J mu k plus 1 because mu k plus 1 is S regular by assumption. Therefore, value iteration from within the set of functions in S, which is J mu k, is n, gives me in the limit J mu k plus 1. So I proved what I wanted, that the new policy is better than the preceding policy. And I have this monotonic decrease towards JS star. So this holds for any sequence that is generated by S regular policies. And we're going to distinguish between two different assumptions relating to PI, strong assumptions and weak assumptions, which lead to corresponding strong and weak results. In particular, we say that S has the weak PI property if there exists some sequence of S regular policies that can be generated by the PI algorithm. So we don't say that every sequence generated by the PI algorithm consists of S regular policies. Here we assume that there exists some sequence. So that's why we call it a weak property. Now let us state a theorem related to this weak PI property. It says that if S has the weak PI property and mu k is a generated sequence of S regular policies by policy iteration, we know that there exists such a sequence by the weak PI property, then this sequence is going to converge monotonically to something, and this something is Js star, and Js star is a fixed point of t. So now the well-behaved theorem applies. So we have that Js star is not only a fixed point of t, but it's the only fixed point of t within the well-behaved region, and value iteration converges to Js star starting from within that region. Let's look briefly at the proof argument. We have that this is a sequence of S regular policies generated by PI. So we have that this sequence is sequence of costs monotonically non-increasing, as we have proved earlier. So J mu k converges monotonically to some limit J infinity, and we have that okay, J mu k plus 1 is a fixed point of T mu k plus 1, and because J mu k is greater than J mu k plus 1, I have this inequality holding. By the definition of mu k plus 1 as the improved policy, I also have that this is true here, and also because T is the infimum over all mu of T mu of J mu k, I have this inequality also holding, which is and I have equality here because mu k is an S regular policy and J mu k is the unique fixed point of T mu k. So I have this string of inequalities, and I take the limit as k goes to infinity. This will converge to J infinity. This will converge to J infinity. Everything in between is going to converge to J infinity. And by continuity here, this is going to converge to Tj infinity. So J infinity is a fixed point of T. And by also using the fact that these sequence is monotonically increasing, there's a simple argument that shows that that we have monotonic decrease all the way to Js star. So J infinity is a fixed point of T. It follows from this, and also by the monotonic decrease of J mu k, I get that the limit is also Js star. Let us now introduce a stronger PI property. We say that S has the strong PI property if it has the weak PI property, and in addition, starting from an S regular policy, PI generates only S regular policies. In other words, you cannot have PI start from a S regular policy and then generate down the line an irregular policy and then back to regular and so on. In other words, the set of S regular policies is non-empty, there is at least one, and it is also closed under PI. In other words, once you start with S regular policies, you continue to generate regular policies. Now, how do you verify these properties, the weak PI property and the strong PI property? For the strong PI property, there's a potent line of analysis which applies for the case where S is the set of all real valued functions over X. And one can prove that the strong PI property holds if there exists at least one S regular policy. And there's a certain compactness property that the control constraint set must satisfy the set of all u that are feasible at any x is such that this set is compact for any real valued lambda, for any x, and for any j in S. This is true in particular if u sub x is finite for every x, also under some easily verified continuity properties when u sub x is compact. Let me not go into the details of this. Let's take it as a compact assumption, which is satisfied fairly easily in various problems. For example, in linear quadratic problems, this compactness relationship is satisfied. Finally, the third assumption, which is the most important, it says that given an S irregular policy, for every j in S, there exists some state x such that the finite horizon costs corresponding to mu with terminal cost function j blows off to infinity for at least one initial state. Among other things, this guarantees that S irregular policies cannot be optimal, because we know that there exists at least one S regular policy whose cost function must be real valued. So J star is real valued, and if I put in here in place of J bar, this says that the cost of mu starting from x is infinite, so mu cannot be optimal. Now let's see what you can prove under the strong PI property, again assuming that S is the set of all real valued functions. So let's assume that the conditions that we gave in the previous slide hold, so that the strong PI property also holds. So we have that there exists at least one regular policy, that there's a certain compactness condition that holds, and also, most importantly, there's an infinite cost condition for irregular policies. An irregular policy cannot be optimal because its cost is infinite from at least one initial state. So assume this condition so that we have the strong PI property, and let's assume also that Js star, the restricted optimal cost function, is real valued and is bounded below. Then nice things happen. We have results that are almost as strong as for contractive or discounted problems with bounded cost per stage. The first result is that Js star is equal to J star, and J star is the unique fixed point of t among real valued functions. So Bellman's equation has a solution, and it's a unique solution among real valued functions. Value iteration converges, starting from any real valued function, converges to J star. There is a necessary and sufficient condition for optimality, which says that a policy mu star is optimal if and only if it attains the minimum in Bellman's equation for every x. Moreover, there exists at least one optimal policy. This is a byproduct of the compactness assumption that as a consequence guarantees that the attainment of the infimum and the existence of at least one optimal policy. Finally, policy iteration works in the sense that starting from an S regular policy mu0, it generates a sequence of S regular policies that monotonically converges to J star. So in this figure here, we have that J star is equal to Js star. Both of them are the unique fixed points of t within the set of real valued functions, and we have convergence of value iteration from anywhere in R sub x, and monotonic convergence of policy iteration to J star. So here we have stronger conditions. Instead of having that Js star is a fixed point of t, we have that both of these are fixed points of t, unique and also equal. We have the convergence of value iteration, and we have the convergence of policy iteration. There's a slight weakness here. In order to apply for this policy iteration result to apply, we have to know an initial regular policy. Such a policy may not be known, and so this may be a slight problem. It turns out that it is possible to bypass this problem by modifying slightly the policy iteration algorithm, but we're going to discuss this in the last lecture. Now let us revisit the deterministic shortest path example where S is the real line, and let us try to illustrate the differences between the weak PI property and the strong PI property. Here we have a single node other than the destination, and at that node we have two choices. One is U that takes us directly to the destination at a cost B. It corresponds to a regular policy, which we denote by mu. And the other control at the other choice at node 1 is a control U prime, which costs A and keeps us at 1. So it involves a cycle, and the corresponding policy mu prime is irregular. The Bellman equation is given by this expression here. And let us now focus on the policy improvement equation, starting with the regular policy mu, which has cost B. Then the policy improvement equation is going to select the control that attains the minimum in this expression, in other words, the minimum between B and A plus B. So if A is equal to 0, both controls can be chosen. In other words, starting from the regular policy, we can generate either the regular policy or the irregular policy. So here we have a situation where the weak PI property holds. It is possible for policy iteration to generate a sequence of regular policies, but it is also possible to generate a sequence of policies that some of which are irregular. So the weak PI property holds, but the strong PI property does not hold. Now let's see what happens when A is equal to 0. We have that the restricted optimum is equal to B, the minimum over the regular policy. The optimal cost is the minimum between B and 0. So if B is positive, then J star is strictly smaller than JS star. The set of fixed points is the set of all numbers that are less or equal to B. The well-behaved region is the region that lies to the right of JS star, is between B and infinity. And because the weak PI property holds, JS star is a fixed point, and it's the unique fixed point within the well-behaved region. The value iteration algorithm will also converge to J star, starting anywhere within the well-behaved region. And the convergence of policy iteration is problematic in the sense that it is possible to generate starting from a regular policy to generate an irregular policy that has strictly larger cost if you don't know how to break the tie in this equation, which you will not be able to know in a more general problem. In this example, of course, it's very simple. So we have these pathologies under the weak PI property, but we also have some good results. In the case where A is greater than 0, then the irregular policy has infinite cost. So all these conditions that guarantee that the strong PI property holds are in effect, and in fact it is very easily verified that starting from the regular policy, we repeat that regular policy, we cannot obtain from this equation the irregular policy. So that's by definition is what we mean by a strong PI property. So now all these good results hold under the strong PI property. In particular, J S star is equal to J star, and J star is the unique fixed point of T within S, which should be contrasted with the case, the earlier case, where we had an infinity of fixed points. Value iteration converges to J star from all initial conditions, not just from the well-behaved region. And policy iteration also works, assuming that we know an initial regular policy, which we do here, but in a more general problem it may be somewhat questionable. Let us now discuss an example, a stochastic shortest path problem, where the state space is finite, consists of the states 1 up to n, plus a termination state t, which is cost-free and absorbing. There are transition probabilities between the states and also from the states to the termination state. The number of controls at each state is finite for all states x, and there is also a cost per state g of x and u, and there is no discounting. Now, an important notion for this problem is the notion of a proper policy. A policy mu is proper if under that policy the termination state is reached with probability 1, or with finite expected number of steps. These two are equivalent. If the policy is not proper, we call it improper. Now let us take S to be the set of all real valued functions over X. So S is Rn because there are n states. Then it can be shown that mu is S regular if and only if it is proper. So the proper policies are the regular policies and vice versa. Another thing that can be proved is that the mapping T mu of a policy is a weighted subnorm contraction if and only if mu is proper. So proper regular contractions are all the same for this shortest path problem. Another thing that can be shown is that if all policies are proper, then the mapping T is a subnorm contraction. Not just T mu, but also T is a subnorm contraction in this case. And then the results are very favorable. Basically, the problem behaves like a discounted problem. Anything that you can prove for these discounted problems, you can prove also for the stochastic shortest path problem if all stationary policies are proper. However, it is possible to have some policies that are proper and some that are improper. So the stochastic shortest path problem is a prime example of a semi-contractive model where some policies are regular and others are not. Let us now summarize the results that we can prove for stochastic shortest path problems. Let's consider two cases. The first case is when the strong PI property holds, and we assume here that there exists at least one proper policy, and for every improper policy mu, there is some state that has infinite cost. Then, because the state space is finite, the control space is finite, and all that, the strong PI property can be shown to hold, and the corresponding results are true. In particular, J star is the unique fixed point of T within Rn, so Bellman's equation holds and has only one solution, namely J star. Value iteration converges to J star starting from every J within Rn. Policy iteration converges to an optimal proper policy if started with a proper policy. It generates proper policies exclusively, and because the strong PI property holds. Now let us consider the other case where there are some improper policies that have a finite cost, perhaps due to zero-length cycles, like in the deterministic shortest path problem that we looked at earlier. Let us call J hat the optimal cost function over the proper stationary policies only, and let's assume that J hat and J star are real valued. In that case, they're also bounded below because S is just Rn. Then the weak PI property can be shown to hold, and by the corresponding theorem we have results which we're going to summarize now. The first result is that j hat is the unique fixed point of t within this well-behaved region. It is not necessarily true that j star is a fixed point of t, and it may be that j star is strictly less than j hat. Value iteration converges to j hat, not j star, starting from any j above j hat. Policy iteration may have problems, as we have seen with the deterministic shortest path example. It may not converge to an optimal policy, even if started with a proper policy. There is also a related line of analysis that applies here, which uses a perturbation line of argument. In particular, we add a positive scalar delta k to G, and then we obtain a problem where the strong PI property holds, and the corresponding results are obtained, namely a unique fixed point within for the mapping T and all the other nice results. And however, the perturbed problem is not the same as the original, but we take the perturbation to go down to 0, and then in the limit we obtain results that are interesting. In particular, there's a perturbed version of policy iteration where we add delta k to G with delta k going to 0. At each iteration we decrease delta k, and we obtain a sequence of proper policies that converge to an optimal policy within the class of proper policies, assuming that we start with a proper policy. There is also another version of PI that we're going to talk about later, which does not require the knowledge of an initial proper policy. And again, for this version of the problem, it is possible to have an improper policy that is overall optimal, and J star need not be a fixed point of T, as we have seen with one of our examples in the preceding lecture. Let us now consider a deterministic optimal control example where the state space is infinite. In particular, we have a discrete time dynamic system which is deterministic, has no disturbance, and there is a non-negative cost per stage. We assume that there is a cost-free and absorbing terminal set of states, capital X0, and the aim is to reach or approach asymptotically this set of states at minimum cost. So this is a problem of regulation to a terminal set of states, like for example the origin. It's a very basic problem in optimal control. Let us take as our set S the set of non-negative functions which are identically 0 within the termination set. And with this assumption, it can be seen that the terminating policies, the ones that reach the termination set in a finite number of steps from all x with optimal cost less than infinity, these termination policies are S regular with this definition of S. There may be some states where J star is infinity. These are the states that where we cannot reach the termination state. We hover around accumulating positive cost, and J star at those states is infinite. Okay, now let us introduce some assumptions that imply that the strong PI property holds. One such assumption is that outside the termination state, the optimal cost is strictly positive. So if we don't reach or asymptotically approach the termination set, you are sure to accumulate an infinite cost. In particular, this implies that S irregular policies that do not terminate have infinite cost. Another assumption is some kind of controllability assumption, where for all states with finite optimal cost and for every epsilon, there is a terminating policy that reaches x0 starting from x with cost that's within epsilon of the optimum. In other words, it's not necessarily true that there exists an optimal terminating policy, but everything that you can do with any other policy, you can also do within epsilon from the termination policy, with a terminating policy, starting from any state. This guarantees that JS star is equal to J star, and because the problem here is deterministic, J star is a fixed point of t, so JS star is a fixed point of t, and that makes things easy. There is also a certain compactness condition which is required to verify that the strong PI property holds, and also to improve the properties of value iteration. The kind of results that you can prove here are, first of all, that J star is the unique fixed point of t, the unique solution of Bellman's equation within S. It's a consequence of the strong PI property. Then we have convergence of value iteration to J star starting from any J within S. Also, policy iteration converges to J star starting from a terminating policy. So these are the standard type of results that you'd expect to hold under the strong PI property. It is possible also to develop a line of analysis that's based on the weak PI property, in which case some of these results here become weaker, but let's not go into that.